gamma, he defined as 1 over the square root of 1 minus the speed of the frame of reference S prime relative to S, which is u squared over c squared. So this is a definition. So these are the Lorentz transformation equations from one set of space-time coordinates to another set of space-time coordinates, right? It's the equations that relate this space-time, space because you got 3 of space and 1 of time, and then this other space-time coordinates as measured by 2 different observers into inertial frames of references. So I think in one of the extra examples, I argued how this can be derived. Okay, I just don't want to do all of that algebra now. It's a good problem for like. So let me maybe make some more room. So if I remember, I think this is correct. I have to double check. But they look good, but I may be wrong also. Ux over c squared, I think, and then gamma is just this factor that I guess you get lazy and you don't want to write again and again. It just shows, this factor shows up a lot. So, and just shorthand notation, so you have this. Well, what if I take these expressions? Notice, t and t prime are not the same anymore. But what if I take these expressions and I write differentials like I did with the other one, right? So we have delta x prime equals gamma, delta x minus u is a constant, and then delta t. And then delta y prime is delta y, delta z prime is delta z, and delta t prime is gamma. Gamma is a constant, right? Remember that u is a constant, and this would be delta t minus u delta x over c squared. Let me just double check to make sure that I'm writing those correct. Jesus, I wrote a lot over here. I guess I just got carried away, sorry. But yeah, they look good to me. All right. Now, what is the x component of the velocity of this object as measured by someone in the green S prime frame? Well, that would be v of x prime. That would be, well, delta x prime over delta t prime, correct? Yeah. The x component of the velocity of the object in the prime frame, in the, let's say in the truck, is delta x prime over delta t prime, right? Using those coordinates for that space. So what would this be? Well, delta x prime is this, so it'll be gamma delta x minus u delta t, and then delta t would be prime would be gamma, and then we have delta t minus u delta x over c squared, right? So notice that the gammas cancel. And what if I divide or multiply this equation by 1 over delta t? In other words, I'm multiplying by 1. I'm just going to divide numerator and denominator by delta t. So I mean, if 1 over delta t is equal to 1 over delta t, so I'm just multiplying this expression by 1, so therefore I'm not changing anything about it, I'm just rewriting it. So this would become delta x over delta t minus u, and then delta t over delta t, right? And then delta t over delta t minus u delta x over delta t divided by c squared, right? This is 1. This is 1. But what is this?
velocity.
X component in whose frame? In this guy's frame, right? It's the unprimed frame. So this is v of x. And what is this? V of x. So this becomes v of x minus u multiplied by 1, and then we have 1 minus u v of x over c squared. So we get the first one. What if I consider, I'm gonna go here. What if I consider v of y prime? What is the y component of the velocity of this object as measured by the green man over here in this frame of reference? It will be delta y prime over delta t prime. Displacement over time. But delta y prime is just delta y. And delta t prime is this gamma, right? And what if I, again, multiply by 1 over delta t and divide by 1 over delta t, numerator and denominator, right? So this becomes what? It becomes delta y over delta t over gamma, and then we have delta t over delta t, which is going to be 1, but I'll write it down anyway, minus u. There's a c squared downstairs, and then I would have a delta x over delta t. But what is this? That's the y component of the velocity as measured by the person on the ground. What is this? The x component of the velocity of the object, right? As measured by someone on the ground. And this, of course, is 1. So we get the second equation. Maybe I'll do this. That the y component equals, notice that we have 1 over gamma, then you have a vy, but then we have 1 minus u v of x over c squared. So this denominator is the same as this denominator. And from symmetry, you can tell that if I did the same thing, because the motion is not on the z-axis, you're going to get that v of z prime equals 1 over gamma, v of z, and then 1 minus u v of x over c squared. So the equation that I wrote on the board about the light beam and the spaceship and the ground, and it was this one. That's the one that I used. Right? Remember when I showed that someone on the rocket would measure the speed of light to be c, and the other person on the ground would also get c for the speed of light? Right? That was this one. Because yeah? By the way, sometimes you want the inverse transformation equations. So if these equations tell me the coordinates x prime, y prime, z prime, and t prime, if I know the coordinates x, y, z, and t, what about the inverse transformation? So it's just a little bit of algebra. And so the inverse transformation it's kind of easy to remember this technique, because then very quickly you can get it without having to do a lot of algebra. Is change the prime by the unprime and the unprime by the prime, but then change those signs. So it would be, for example, if I want to know x, it would be gamma, and then I took away the prime, and now this is, then I would put x prime, but then I have to change the sign, and this is u t prime. And this one, well, I just bring this here and this over there. So y equals y. This one, I just bring this here and this over there. So z equals z prime. And then this one, I get rid of the prime. But then I put the prime on that one. And I gotta put a plus over there, u x prime over c squared. So this is the inverse transformation equations.
Did you forget a y prime in the?
Huh?
For the y prime, I think you forgot that.
It's an invisible y prime. Thank you. Now, interestingly enough, what were the transformation equations for Galileo? The Galilean transformation equations? So the Galilean transformation equations, right? They were what? X prime is x minus ut, y prime equals y, z prime equals z, and t prime equals t. Now, when were these good? Right? When u is much less than the speed of light, right? So what would happen if I wrote these equations, if I consider the Einstein-Lorentz transformation equations, and I made u very small compared to the speed of light? So, what becomes of gamma? Gamma is 1 over the square root of 1 minus u squared over c squared. So what if u is much less than the speed of light? I can think of this as 1 over the square root of 1 minus and then the square of u over c. But if u is very small compared to the speed of light, this is very small, and on top of that I square it, so essentially this goes to 0. It approximates to 0. And so then I get 1 minus 0, which is 1. The square root of 1 is 1. 1 over 1 is just 1. So this equation will become 1 times x minus ut, which is this. This equation, Lorentz transformation equation, will become y prime equals y. That's the same. Z prime equals z. But what about this one? Right? Then this would become 1. Gamma will become 1. Now, but notice, u is small, right, compared to the speed of light. So u over c squared is like, this is out. So this becomes 1, and therefore t prime equals t, which is that. It's cool. I mean, if you think about it, right? If you take the limit as u is much less than c, right, you get that. So in other words, it's not like Einstein said this is totally wrong. He said it's good, only in the limit of the speeds involved are very small compared to the speed of light. Then you're good. It's fine. I'll accept it. But if the speeds involved are close to the speed of light, then it's not good. It's gotta be this. So he was able to, because this was known to work in experiments where the speeds involved were small compared to the speed of light. So something was good about that, right? Because they worked. Right? So what Einstein just did was expand on it and write a more general transformation equations from one set of space-time coordinates to the other one. Right? That would give you the correct result in the limits of, speeds are very high, close to the speed of light, and also it would just give you back the results that people had shown that this was good to be in the limit of the speeds being very small compared to the speed of light. Now, how do I want to say the next thing, right? Okay, let me say it like this. There's so many different arguments. I used an argument over here that took pages, but I don't want to do that. I just want to show you, I want to present you with a different argument. Okay, let me show you, let me focus on this formula right here. Okay? Let me erase this over here, okay? Can I erase this? I'm just showing you a lot of, this is, notice this, I haven't done any badass integral or, difficult partial differential equations, right? I just took delta x over delta t. I mean, it's algebra. It's high school stuff, right? It's high school stuff. Or high school math.